The next set of circuits we're going to talk about is capacitor circuits. So capacitor circuits are essentially where we take, you can think of it as, so this part represents two large plates with a spaced gapping in between the circuit, where essentially we allow the charges to pool up on either side. So for this case, I want you to think about electric fields whenever we're dealing with this. And you can think of, so the positive charges will pile up and pool up on this side of the plate, and the negative charges will pool up on this side of the plate. And that actually has to deal with the direction in which the charges flow. The charge is equal to the capacitance of the specific capacitor times the voltage of this at that specific point in the circuit. Now, voltage is the same across a capacitor circuit like it was a resistor circuit. So if the capacitors are in series, just like with the resistors, the voltage adds across the circuit. So for this case, this is an in-series set of capacitors where voltage adds across the circuit, okay? The unit for charge, so Q is the charge, the unit for charge is Coulomb. And I want you to think of, what does that unit mean? 1 Coulomb is equal to 6.2 times 10 to the 18 elementary charges. And what is an elementary charge? That is essentially 1 electron. So you can think of 1 Coulomb is 6.2 times 10 to the 18 electrons. And the reason for this conversion is, there's two reasons. The first reason is it changes the sign from a negative to a positive. The charges of electrons, if you think back in chemistry, the charges of electrons are negative. The proton is positive. But because of the way we build circuits, and it's just a little bit more uniform to represent it this way, that changes the sign from then positive to negative. So now that's why current flows on a circuit positive to negative instead of negative to positive, because we've switched it to the unit of coulombs, and it accounts for that change. The second reason is electrons are small. They're very, very small. So in order to kind of get more realistic measures on something we can see when we're building like a circuit, we're dealing with a lot of electrons. We're dealing with, 1 Coulomb is 6.2 times 10 to the 18 electrons. It's a lot of electrons. So the other unit is just to make it a little something more manageable that we can actually use to build a circuit, because we're never really talking about just 1 electron. So instead of dealing with current for a capacitor circuit, so like we dealt with in resistor circuits, for capacitor circuits we are dealing with charges. And actually they react the same way as the current does for an in-series set. So in this case, for in-series capacitors, the charge is constant. So we're going to look at a few examples to get essentially what we did before with the resistors. We're going to fill out with the table here. We're going to label this the capacitor 1, capacitor 2, and capacitor 3. And this will be our total voltage of the system connected to some power source. The capacitor is opposite of what the resistors were. So if you remember back in our video before, the resistors, when they're in series, is simply the sum. They just add across the circuit. For capacitors, when they're in series, it's the inverse sum of the inverses. So you can call it total capacitance, or the other term is total equivalence. You can say the same thing for resistors, total resistance, or the resistance equivalence, which is essentially the overall resistance or capacitance of the circuit we're specifically dealing with. So in this case, we could call it the equivalent capacitance, then going to be equal to 1 over the capacitance of 1, plus 1 over the capacitance of 2, plus 1 over the capacitance of 3, and all of that is inversed. The units for which, often, not always in the case, but in this specific instance, are going to be in microfarad. They're very small. So if I'm going to represent it like this, oftentimes the most common unit you'll see for this is microfarad. And again, for voltage, the unit is volts. And then we talked about coulombs being the unit for charges, which again is akin to 6.2 times 10 to the 18 electrons. So we can calculate the total capacitance by simply plugging this in. We have 1 over 20 microfarad plus 1 over 10 microfarad plus 1 over 5 microfarad. all of that to the -1. If we plug into our calculator, we get that it is roughly rounding right here, so 2.86 microfarad. So this is 2.86 microfarad. Then we can use our equation that the charge is equal to the capacitance times the voltage to figure out essentially our missing charge. So our charge equivalent, or total charge, is going to equal the equivalent capacitance, but in terms of calculating charge properly for coulombs, I need capacitance to be in Faraday, not microfarad, so I need to take that into account. So it's 2.86 times 10 to the -6 Faraday times the voltage of 15 volts. And I get that it is roughly 4.29 times 10 to the -5 not microcoulombs, coulombs, or I could write it like this, 42.9 microcoulombs. So 42.9 microcoulombs. The next capacitor circuit we're going to look at is when all the capacitors are in parallel. So when they are in parallel, they're opposite, right? So parallel voltage is still the same. So voltage is constant in parallel circuits. So voltage is constant. And then it's going to be the opposite for the series one, right? So we have the charge equals the capacitance times the voltage. In this case, the charge adds. It's no longer constant. So charge adds. And the capacitance, the total capacitance or equivalent capacitance, is simply the sum of all the capacitors. So we can call this one C1, C2, C3, and then again this is the total voltage from the power source. Alright, so in this case our total capacitance is just going to be adding them all together. So in this case it'd be C1 plus C2 plus C3. We're going to look at some actual examples. So go ahead and pull up a table here. And we're going to go ahead and kind of fill it out. Here we can then calculate the total capacitance for this specific example. If you notice, our capacitor values are actually the same and we've pumped in the same amount of voltage, but because this is in parallel, our total capacitance is going to be quite a bit different. So in this case, total capacitance is going to be just the 20 microfarad plus, so these are again all microfarad, and then this one is also voltage. So then it's plus 10 microfarad plus 5 microfarad, and we get that it is 35 microfarad. So the other thing we can note, and again, so because this is all in parallel, the voltage is constant. So each of these is 15 volts. 15 volts, 15 volts. And then using our charge equation, right? Q equals CV, we can then calculate the independent charges. So we can calculate the total charge, QT, to be the total capacitance times the total voltage, which I can calculate then. So my total capacitance as 35 times 10 to the -6 Faraday multiplied by the voltage, which is 15 volts, and I get that my charge is 52, or you could put it like this, it's 5.25 times 10 to the -4 coulombs. We could write it as 525 microcoulombs. So 525 microcoulombs. And then I can do the same thing with essentially all of the other charges. So Q1 equals C1 V1, which in this case is going to be 20 times 10 to the -6 Faraday times 15 volts. And I get 3 times 10 to the -4 coulombs, or 300 microcoulombs. I'm going to do the same thing for Q2 equaling C2 V2, which is 10 times 10 to the negative 6 Faraday times 15 volts. Get 1.5 times 10 to the negative 4 coulombs, or 150 microcoulombs. Sorry, I keep writing F. It should be coulombs. See? And then I can calculate Q3 by either plugging it into the same equation or noting, since charge adds, the total charge Q total is the sum of all of the charges. So Q3 is going to equal Q total minus Q1 minus Q2, which is 525 minus 300 minus 150, and I get 75 microcoulombs. Just like we looked at what happens when we have a circuit with the resistors where they're both in series and parallel, we're going to do the same thing for the capacitors. The equation for total capacitance or equivalent capacitance is actually quite a bit more tricky, but we're going to walk through it and hopefully it'll make some sense. If you're ever in doubt on how to figure out the capacitance equivalence for that, breaking it down in steps is actually a lot easier, but I'm going to show you the overall general equation, so hopefully that kind of makes sense. Let's first, though, we've got to remember that still the charge is equal to the capacitance times the voltage. That is still true. In this case, so because we remember that charge is constant in series, right, and adds in parallel. So the charge total is going to equal the charge of the first, across the first capacitor. And then that is going to equal the charge across the second capacitor plus either the charge across the third or the fourth. So you could write it like this, so plus the charge across the third, where the charge of the third is equal to the charge of the fourth. That's because 3 and 4 are in series to each other. So it doesn't matter which one I add to the what is in parallel to charge across to. Then I can think of the voltage adds across in series, so V total is going to equal V1 plus this whole set right here, whatever the voltage is at that point. Since voltage is constant in parallel, I can say that all of that is then equal, so plus V2, where the sum, so V2 is equal to the sum of V3 plus V4. So those are our equations thus far for the voltage and the charge. And now let's look at what is the equivalent capacitance. So again, I said this equation is a little tricky, but we'll kind of bear with it because, so remember, the in series is the inverse sum of the inverses, and then the in parallel is what adds. So we can say that the equivalent capacitance is equal to, because C1 and this whole section C2, 3, 4, right, that combination of that junction is in series to each other. We're going to then essentially say that this is going to be 1 over C, and actually maybe I better write it like this just for the sake of saving space. We'll say C1 to the negative 1. That's the same as saying 1 over C1. And we're going to add that to essentially the C, I'm going to call it 2, 3, 4 for now. And that's also inversed. And then all of that is inversed. So then we're going to kind of do this in steps so you can kind of see where we're going with it. So it makes sense because, again, this one is a tricky setup. Okay, so then I get essentially, well, what is this C2, 3, 4, right? So C2 is in parallel with C3, C4. So I can kind of write this as essentially C2, 3, 4 is equal to C2 plus C3, 4. I can kind of write it like that. I can then specify, well, C3, 4 is equal to essentially C3 inverse plus C4 inverse, and all of that inversed, because those two are in series with each other. And then if I plug this all back into the main equation, I get that the equivalent capacitance is equal to, make a big enough parenthesis here, C1 inverse plus, get the parentheses right, so we've got C2 plus, bear with me, C3 inverse plus C4 inverse. That is inversed, and then I close that parenthesis, that's inversed, and then I close the last parenthesis, which is inversed. So you can see why this is not as straightforward. So we can go ahead and then calculate the actual total capacitance for this equation. Again, also equivalent capacitance. I'm using those interchangeably. So the equivalent capacitance is equal to then, I'm saying the inverse of 10. So essentially 10 to the negative 1 plus, and just for sake of space, so we know that the unit is microfarad, which I'm not going to put in the equation just for the sake of space because this one's going to be a little bulky. So plus, then in parentheses, I've got 8. This has not been inversed yet, so it's 8 plus, and then I'm going to inverse it at the end. So that stays 8, plus the inverse of 3, which is 5 inverse, plus the inverse of 4, which is 3 inverse. That gets inversed, close it, that gets inversed, close it, that gets inversed. So if I put it in my calculator properly, I get the equivalent capacitance to be somewhere around 4.97 microfarad. So 4.97 microfarad. Once we've calculated the equivalent capacitance, we can then figure that out, use that to figure out the total charge. So charge total is equal to capacitance total times voltage total, which in this case I'm going to have it as 4.97 times 10 to the negative 6 Faraday times 15 volts. And I get that it is 74.5 microcoulombs. Now if we remember that the charge across the total charge is the same as the charge across one, so those are in series and they are therefore consistent, then the charge across one is the same. I can then use the same equation if I re-solve the variables for voltage equaling the charge over, not the voltage, sorry, over the capacitance for the voltage across one. I get that I have 74.5 microcoulombs divided by 10 microfarad. And I get that it is 7.45 volts. I can then use the fact that I know that the total voltage is the sum of the voltages across 1 and 2 to figure out what the voltage across 2 is. So V2 is equal to V total minus V1. So that's going to give me 15 volts minus 7.45 volts. And I get 7.55 volts. And then use the same equation to find charge. So charge across 2 equals capacitance across 2 times voltage across 2. So that's going to be 8 times 10 to the negative 6 Faraday multiplied by 7.55 volts. And I get that that is 60 microcoulombs. I can then use the equation that I know, Q total equals Q1, which is equal to Q2 plus Q3, to find Q3. So Q3 is going to equal Q1 minus Q2. And that's going to give me the 74.5 microcoulombs minus 60 microcoulombs. And I get 14.5 microcoulombs for Q3. And then I know that Q3 is equal to Q4 because those are in series. So this one's also 14.5 microcoulombs. And then I can use the voltage equation to figure out the voltage across 3. So the voltage across 3 is equal to the charge across 3 over the capacitance across 3. So the charge across 3 is the 14.5 microcoulombs over the capacitance across 3, which is 5 microcoulombs. And I get that it is 2.9 volts. So 2.9 volts. And then I can use either the same equation to figure out the voltage across 4, or I could use the fact that I know voltage of 2 is equal to the voltage of 3 plus 4. So V4 equals V2 minus V3. So it's going to be 7.55 volts minus 2.9 volts. I get 4.65 volts. And again, it doesn't matter which equation I would use, it'd get to roughly the same value. Again, with any minor discrepancies just being from rounding errors.